Welcome everyone to BigML's Fall 2015 webinar. So our last webinar was back in February, and since then we've brought a lot of new features and algorithms to the BigML platform. So today we're going to demo some of the most exciting things that we've introduced as part of this fall release, including our highlight, association discovery. So back in July, BigML acquired Jeff Webb's popular association discovery software Magnum Opus, and we're really excited to be releasing it today as part of our core platform. Association discovery is a powerful tool for exploring unlabeled data, capable of uncovering interesting relations between variables in your data. So let's take a quick look at the BigML workflow to see how association discovery complements our existing platform. So BigML's workflow always begins with what we call the source step, and this is where the data is uploaded to BigML and the field types are auto-detected and then corrected if necessary. The next step is to create a data set from the source. Data sets are the fundamental building blocks for all of the machine learning algorithms in BigML. For supervised learning, this is when you would build a model that tries to predict a specific label in your data. And for that, BigML currently offers decision trees and ensembles of trees, as well as logistic regression, which we'll be introducing later. In the unsupervised learning space, the BigML platform offers clustering in the form of k-means and g-means, where g-means has the ability to automatically discover the appropriate k-value for your data. And in anomaly detection, we have the isolation forest. So our new association discovery algorithm is also unsupervised learning. So how is it different from clustering and anomaly detection? Let's take an example just with some fake transactional data. So here we have some customers and account numbers and purchases that are being made. Perhaps this is credit card data. In that first example, what we have is in clustering, the goal is to find your instances. In this case, that is a complete row that are similar. So as a simple example, looking at this financial data, we can see the transactions highlighted in green there are both occurring on a Wednesday from the customer Sally and purchasing gas for almost the same amount. And so a clustering algorithm would be looking for instances in your data that are similar in that way. And in this particular case, even though the zip code is different, then these purchase, it looks maybe Sally's going on a road trip, right? But anyways, those transactions are very similar. So in anomaly detection, the goal is to look for instances, again, a complete row, that are very unlike all the other rows. Hopefully you can detect this in a multi-dimensional way. So you don't want to look at each variable individually. You want to be able to say it's anomalous across a set of variables, which is one of the nice things isolation forest does. And we can kind of see in that highlighted example there, Bob has made this rather unusual for his history of transactions, an unusual technology purchase for a very large amount compared to his other transactions. And also, it's in a zip code he doesn't usually buy things in. So maybe Sally's on a road trip with Bob's debit card. All right, so let's look at this same data with the idea of association discovery. So the first thing to notice is that we do away with considering rows atomically. That is, we look for associations between features inside each row. So in the highlighted examples, we see that Bob has made several purchases on his account number 3421 in zip 46140. So we could write this discovery as a rule. That is, if the customer is Bob and the account is 3421, then the zip is 46140. Now you'll notice this isn't always true, that the third entry there, the zip is actually 21350, and that's okay. The rules don't have to be always true, right? This is just going to alter the strength of this association, if you will. And we can also see a second example in there of these two gas purchases. And now we could imagine a rule that if the purchase class is gas, then the amount will be greater than $80. Although gas prices have been falling lately, so maybe that would be hard to imagine right now, a very large car. Okay, so let's put a little bit of terminology onto this. We can see down at the bottom, we have our two rules that we've discovered by looking at the data. And what we call these rules is they consist of the match criteria on the left-hand side, which we refer to as the antecedent. And when the antecedent is matched, the rule indicates that there is an output on the right-hand side, which we call the consequent. So an important thing to notice at this step is that the antecedent can contain multiple criteria, like in the example above where the customer is Bob and the account number is 3421. However, the consequent is always a single criteria. So the process of association discovery then is to scan through all of your data and find these types of rules, where the antecedent is implying a consequent. And as you're doing this, you need to collect some statistical information that allows you to determine which of these rules are significant and which are therefore uninteresting or interesting if they're statistically significant. All right, so what is association discovery useful for? One of the big use cases is market basket analysis. So the idea here is to look at transactional data where each transaction contains multiple items. And you want to be able to answer the question, what items tend to occur together in a transaction? So the classic example, although it's probably apocryphal, is the beer and diapers analysis. And if you Google that, you'll hit lots and lots of pages talking about this, where there's allegedly this strong coincidence of men buying beer and diapers at the same time. You know, and is it newborns and the wife is sending the husband to get diapers and he's buying beer because he hasn't slept in 3 days? You know, there's a whole bunch of studies. Although it appears to not actually be a true study, it's a perfect example of the idea of association discovery, right? Mining what looks like uninteresting data and then finding these interesting relationships, because that would be somewhat surprising. So web usage data is another good application of association discovery. And the idea here is to look for correlations involving user behavior or profile information on a website. Similarly, intrusion detection, you can imagine discovering a rule indicating that your system administrators always log in from a certain subnet or perhaps a certain group of servers. And now you're monitoring logins in real time, and if you see one that violates these rules, then you might mark that as suspicious, so follow up on that. Fraud detection could of course work similarly, right? You could mine these association rules for consumer behavior and then mark deviations. Bioinformatics uses association discovery to look for meaningful associations in, for example, genomic data. And finally, this idea of medical risk factors, which is actually one of the examples we'll look at as well. So obviously this isn't an exhaustive list, but let's dive into a couple of these. So since it's such a common use case, let's take a look at market basket association. So, or a market basket analysis. We'll do this quite literally, and we'll consider a data set which consists of grocery store transactions, where each transaction includes a set of items that the user bought in one trip. So you can imagine they're all in the cart, and they go through the checkout, and you just mark down everything that was in the cart, and that becomes a transaction. And the goal is going to be to discover interesting rules about what store items are typically purchased together. Now, although we're playing with this grocery data, keep in mind that, of course, this could be any basket-related transaction data. For example, an e-commerce site or a software-as-a-service platform. And run that. So this is our data set, which I've just uploaded into BigML in our source step. And I'll show you what the contents look like. All right, so we have a single feature. There's just one feature. If you think about this in terms of your traditional CSV, it just has one column. All right, and that feature is called the cart. And you'll notice that we've automatically detected this field type as being items. This is a new field type for BigML. Previously, we had numeric, categorical, unstructured text fields, and date times, which we parse for you automatically. We'll see one of those too. But so items is a new field type that basically allows the BigML engine to look inside of what looks like a single column and find multiple features in there. And then we can kind of see some examples of what's in there, right? So in the first row, you imagine, again, this is a cart with a single transaction. We have somebody bought citrus fruit, semi-finished bread, margarine, and ready soups. And here we have another tropical fruit, yogurt, and coffee. Some of these transactions are small, like this person only purchased milk, where this person also purchased milk, butter, yogurt, rice, and an abrasive cleaner, for example. Okay. Now, again, this being the configure step, this is where we need to make sure these field types are correct. And the one thing I want to point out here is there's two types of separators now. So the first on the left-hand side here is the actual feature separator. So you can imagine, again, if you're uploading a CSV, a comma-separated field, it's not always separated by commas. You know, sometimes it might be separated by semicolons. We've seen cases people using pipes. And so this is where you are informing the source engine how the features are separated in your data set, or in your data. And then we also have an item separator. So inside of a specific feature, you can say, look, the item separator is a comma, and now it'll be able to take a single column known by the CSV separator and find items inside. All right, so you can experiment a little bit with this. I've seen cases where you have a data set where instead of the items being all in one field, they're broken across columns, and so you can actually fix that by setting the source separator to a non-existent character, like a pipe, for example, if you don't have pipes in there. And that will now squish all the features together into a single column, and now I can force the item separator to be comma, and that will break my items back apart. So I've taken multiple columns into a single column and then brought the items back out. All right, we don't need to do any of that stuff in here, so I'm just going to go ahead and reset that. And we'll go ahead to the data set. All right. So this is processed very similar to a text field, so we can actually see the item occurrences, right? So we got the whole milk has occurred 2,513 times, and we can even see this using a nice tag cloud, so we can get a visual representation of how common each of the items are that we're discovering in these carts. Right? So we can see whole milk is, of course, an extremely dominant item that people are buying in the store. We also have things like canned beer and root vegetables and bottled beer, etc. Okay, and from here, what we're going to do is we're just going to go straight to what we call our one-click association, and this is going to just take the default parameters and train association discovery. So again, what it's doing now is it's going to search through each one of the rows and look at each cart, and then across the rows, it's going to try to find common associations, right? Things that if you're buying this, it implies you're probably also buying this as well. And you can imagine from a grocery store perspective, this might be something where you want to analyze how to co-market things, right? If you have a sale on one item, you might want to have a sale on the other item. You know, people are going to buy together. You might position them in the store, or you might be evil and try to position them far apart in the store so that people have to go past your sale aisle or something. There's lots of things you could do with this rule. For this, we're just more focused on creating the rules. So now we have these. What we're seeing here is the list of the rules it discovered. So we can see on the left-hand column here the antecedents, and of course then the consequent. Right, so this is, if you have this, it's implying this. And then we have these 5 additional metrics, and I'm going to go into these in much deeper analysis when we return to the slides. So I'll just kind of give you a little bit of hand waving right now. But basically, we can see this very first rule. We have this idea, other vegetables implying root vegetables, right? So if you're buying, broccoli and cabbage or something, maybe you're also buying carrots, which are probably the classic example of a root vegetable. And this rule has what we call a coverage of 19%. And that means that this antecedent here, the other vegetables, occurs in 19.3% of all of the carts. All right, so it's a very common item. All right, and then the confidence is basically telling you how likely this rule is, how likely it is that when you do have other vegetables, you have the root vegetables in there as well. All right. So one other thing we can do that's interesting here is we can just sort this by this lift field, and we can see another example of a rule. So this is, now we have an example of people who are buying beef, okay, they have beef in their cart, are also buying root vegetables, which again are typically like carrots. And so you can imagine this might be a North American grocery outlet, because this is a pretty traditional North American dish, right, beef with carrots. And this is, we'll explain the lift a little bit more. But you'll also notice that every rule has a complementary rule. So beef can imply root vegetables, but also buying root vegetables can imply beef. But you'll notice that the metrics aren't the same. And that's to be expected, because they, of course, are occurring in different frequencies, right? So here we can see the number of carts where people are buying beef is only 5%. But the number of carts where people are buying root vegetables is nearly 11%. Now they do have the same support, but the confidence is going to be different because they're not bidirectional rules, right? One implying the other does not necessarily mean that the complementary is true. The complement is true. All right, we can also visualize this in terms of a graph. And this, what we're seeing in the graph here is a visual representation of these rules. So each one of these nodes is an item, and it's connected to another item. So we can actually dial this so I can show you a couple examples. So here we have a rule where rolls and buns are being associated with sausage. And remember, I was explaining that rule is bidirectional. So this is a bidirectional association, right? One implies the other. And you can the width of the line here is proportional to the search strategy, which we haven't talked about yet, but we will. And also that's how you can filter as well. So the leverage in this case is how we determined or how we detected these rules, and so this line thickness here is representing this association between other vegetables, and in this example, whole milk has a very high leverage. We can actually zoom this down a bit more. We can see kind of this little set of rules here where other vegetables and yogurt and whole milk are all associated with each other. I believe if we dial this out just a touch, I can find this pairing here. So now we have, in this case, we have whole milk. When people are buying whole milk, they're typically buying curd, butter, and domestic eggs. So this is, pretty much people that are doing a dairy run, right? They're going to the dairy aisle and buying all of their dairy products. And you can see those are all being associated with whole milk. So that's really the most common dairy item there, being associated to everything else. A couple of things you could do in here is you can actually control the fields that are shown here. In this case, we only have one. You can, of course, pull this down as an image, and you can label these as well if you want to see what's going on. If you want to see what the name of each node is. The only reason you can turn that off is, of course, because you can have a very complex picture like this, and it gets a little tricky. This is kind of fun because you can actually drag this around a little bit and change the visualization. And you'll notice that sometimes as you dial this, you get these sort of detached associations as well, which is fun. Bottled water and soda. All right, so let's dive into these metrics a little bit and get an explanation, slightly better explanation of what those mean. Okay, so the first is the coverage, which we sort of already talked about a bit. But if you just imagine all of the instances in that big circle there, and then in your mind you consider that we have a single rule that we're talking about, where an antecedent, that is the A, implies a consequent C. All right, and so all of the instances that contain the antecedent are represented by that big green circle with the A in it. And all of the instances that actually contain the consequent are in the circle with the C, okay? And the coverage of this rule is the percentage of the instances which match the antecedent. In this case, that's the area that's green. So it's literally just how much of your total data that you're analyzing does the antecedent apply to, right? So if you have a small coverage, this is a rule whose antecedent doesn't occur very often. If you have a large coverage, it's a rule whose antecedent occurs very often. All right, and then we have the idea of support. And support now is the percentage of the instances which match the antecedent. And remember, the rule implies a consequent, and so it's the percentage that has both. Right? This is really the percentage of instances that match your rule, okay, where the antecedent and the consequent are both in the item. And in this case, that is sort of is exactly the green shaded area. So the support is where those sets intersect, and we have all the items that have both the antecedent and the consequent. So these are all examples in your data set that match the rule. And now we can talk about confidence. So confidence is a percentage of instances in the antecedent which also contain the consequent. So now instead of looking at support as a percentage of, instead of thinking about support as a percentage of all the instances, we're thinking about it as just a percentage of the antecedent. All right, so this is giving you a measure of how many or basically the strength of how well the antecedent implies the consequent. And you can imagine looking at the ratio there that this is computed by support divided by coverage, and so if they're equal, then you're going to get a confidence of 1, whereas if they're separate, you're going to get a confidence of 0 if those two sets are separate. So we can visualize what I just said a little better by sort of imagining the grade of how well these sets intersect and looking at what the confidence would be, right? So if A and C don't overlap at all, then A never implies C, and therefore you can see that there's no intersection, so the support is 0. So you have 0 divided by a positive number, that's 0, so the confidence will be 0. And then in the middle, we have some kind of an intersection all the way to the consequent being fully contained. And those are all confidence less than 100%. And that might be a little surprising at first why the consequent, if it fits fully inside A, why the confidence still isn't 100%. And this is because you have examples now where the antecedent doesn't imply the consequent, right? Those are sort of that moon shape, the gray moon shape in that middle picture. Okay, because you can imagine if A implies C, then C, not C, must imply not A. And we certainly have cases here where not C does imply A. Okay, so we know the confidence can't be 100% there. So if the confidence is 100%, that means these sets are basically either the same, okay, they contain all the same instances, or the consequent is actually larger. That would be another case where the confidence could be 100%, because now all of the antecedents imply the consequent always, and so the confidence is 100%. So either of those two examples on the right-hand side would be a confidence of 100%. So lift is another metric, and what we're getting with lift is now we're looking at how well this rule, how statistically significant this rule is. That's what this metric is trying to give you a better indication of. And what we're going to do is we'll compute the ratio of the observed support, so when we actually go through and count what the support is, and we're going to divide that by the support if A and C were statistically independent. I mean, if they're statistically independent, they're still going to have some overlap just by randomness, okay? And so we can measure that, and we can compare it with how much overlap we actually see. And so you can see how this is computed. This is literally the support that we've already discussed, and divided by the product of their two probabilities. That's sort of the traditional way of computing the support for two independent variables. And it's worth pointing out that you can also compute this by just by substituting the definition of support, or by confidence, that you can also compute this as the confidence divided by the probability of the consequent. And this is important because if you look at that equation on the right-hand side there, confidence divided by the probability of the consequent, if the probability of the consequent is very low, you can end up with a high lift, even if the confidence is also low. So that this is sort of one of the things to watch for when using lift, and I'll show an example of that so it may be a little bit more clear. But let's visualize this pictorially. All right, so on the left-hand side, so the bottom sets here are the case where we imagine the antecedent and consequent are independent. Okay, so it's the same there all the time. And then the top is what we observe. And so if we observe that they're actually completely disjoint there, they have a support of 0. And so we're going to take 0 and divide it by a positive number. And we're going to get a number that's less than 1. So that, and this is telling you is a negative correlation, right? A implying C is actually negatively correlated. It's even less likely than if they were statistically independent, which is possibly interesting. And then if they're exactly the same, if we say this is what the support would be if they were independent, and we observe the same support, then we get 1, and so the lift is 1, and there's no association between those. And then on the right-hand side, we have a case where we see a much stronger correlation than if they were statistically independent. And so when we divide the support that we observe by the support if they were independent, we get a number larger than 1, and this would be now a positive correlation. And of course, those are typically the rules that we're going to be interested in looking for, right? Things where we observe a better correlation than we would expect if they were independent.
And so another metric we can use to think about the quality of the rule is called the leverage. And this is similar to the lift in that we're still interested in the observed support and the support if the antecedent and consequent were statistically independent. But now instead of taking the ratio like we do in lift, we subtract them. So we take the observed support and we subtract the support we would expect if they were statistically independent. We can think about what this rule means pictorially again. So on the far left-hand side, we have the situation where the antecedent and consequent are completely disjoint. And so the support will be 0, and we subtract the support if they were statistically independent, which will be a positive number. So we get a negative number between -1 and 0. This is telling us there's a negative correlation. In the center, we have the case where the observed support is the same as the support we would expect. If they were statistically independent, we subtract two numbers of the same, we get a leverage of 0, so it's telling us no association. And the far right-hand side, we have a much higher observed support than we would expect if they were statistically independent. And so we take a large number and subtract a smaller number, and we get a number greater than 0, but still less than 1, indicating a positive correlation. And so the leverage is always ranging between -1 and 1.
All right, so let's return to our example data, and play with this a little bit. So we can come back to our grocery data set. And I'm going to show you some of the instead of doing the one-click association, we'll drill into this a little bit and actually configure an association so you can see the options. And this will highlight a little bit of how this algorithm actually works. So the first thing, considering those 5 metrics that you can change, is the search strategy. And this is basically telling the association discovery engine how to optimize what it keeps while it's analyzing these rules. And so by default, we use leverage, but you can change this. So if you want to optimize your rules based on something else, like you want to see rules that have a higher lift or see rules that have higher confidence, then you can change your search strategy here, and now it's going to keep rules that have that metric that have higher values. So for this example, we're actually going to change that to lift. The other thing you can change is the maximum number of associations. So if you just sort of visualize this as a buffer, it's going through and finding all of these potential rules where some antecedent implies some consequent. It's computing all these metrics, and then it's taking the search strategy that you've indicated and seeing whether or not the metric for this rule it's discovered beats all the other rules. And if it has, it replaces one. And here is where you can tell it how many it should have at the end. So basically telling it how many rules should be in the buffer, and you can adjust that. You can also change the maximum numbers in an antecedent. So you can imagine if you had 100 features in your data set and you wanted, you tried to look at all possible associations of all 100 features, that would be a very computationally intensive task. And so you can restrict this here and say, look, don't ever go deeper than 4 when you're considering how many rules can be in the antecedent. That's the default, but of course you can adjust this anywhere from 1 to 10 currently. You can also add complementary items. So this allows you to have rules where you say the antecedent is not true. So you can imagine you might discover a rule, or maybe you are testing a rule that's milk and coffee implies that somebody is going to buy sugar. And you could say, well, what about milk and not coffee? Does that still imply sugar? Well, if you add this option, it'll automatically search for those types of rules as well. In the advanced configuration, you can set some measures. So this allows you, even though we're optimizing our search by lift, you can also say, while you're considering all those rules, even if it has a high lift, don't even consider it unless it has a specific level of support or a specific level of confidence or a specific level of leverage. So I can set minimum criteria for the other metrics, even though I'm optimizing, in this case, by a lift search. And then the last option I want to talk about is the discretization. So you can imagine if you have a numeric field, 0 to 100, there's literally infinitely many possible values in there. So when we're building antecedents for a numeric field, we have to discretize. We have to break it down into buckets, essentially. And enabling this pretty option just makes sure that the boundaries we use look nice, right? So you don't end up with 26.43 or something. You get a nice rounded human lovable barriers or distinctions. All right, so let's go ahead and create this association, but now optimized by lift, so we can see how the rules change. And again, we're now going through the entire data set and computing, or trying to find these rules and computing and optimizing by lift. So now we expect to be able to find some very high lift rules. And we can actually, this is sorted by lift, so we can see a few examples right at the top here. And the one that I'm going to dive into a little bit is sort of this rule here where baking powder is indicating, when somebody's buying baking powder, indicates they're buying cooking chocolate as well. And this is interesting. Maybe they're making chocolate cake. It's not too surprising. And this does have a very high lift. But let's look at the metrics and apply some of the knowledge that we have now about how these are computed to look at how we ended up with such a high lift. And so the interesting one to me is that you've got this rule here that has a very low confidence, right? It's 4%. Remember, confidence is telling you how strong this correlation, if you will, is that baking powder is going to indicate chocolate. So it has a very low confidence, but we still end up with a high lift. All right, so what's happening there? Well, remember, this can happen if the probability of the consequent is low. And because we have these complementary rules, we have the opposite, or the complementary rule right below it, right? So baking powder implies chocolate. We also can see that cooking chocolate implies baking powder. And the probability of the consequent is the coverage of this rule, right? Because this is the consequent, and down here it's the antecedent, and the coverage of the antecedent is telling us that's the percentage of instances that contain it. And so we can see, if you just imagine how this is computed, we're going to take a 4% confidence, and we're going to divide it by 0.25%, and we're going to get 16. So that's how we end up with that high lift, even though we have this low confidence, if you will. And basically, the reason why this might be important to you is that this rule, covering this cooking chocolate, it doesn't really occur that often, right? It's 0.25% of all the carts contain this item. So this is what you might consider a fairly rare occurrence. And even though it has a high lift, it may or may not be interesting. That sounds like a bit of hand waving, but this is just discovering the properties of your data. What is interesting is kind of still the human side, right? I mean, the computer can analyze the data and say, here's all the things I discovered, and then we can look at it and go, oh, that's interesting because we didn't expect it, or that's interesting because we expected something else. The machine learning algorithm doesn't have a deeper understanding of baking powder or cooking chocolate, or why this rule might be important or might not. And so that's where you have to bring kind of your own analysis, and you have to be a little bit of aware of what these metrics are telling you, or it's good to be aware. All right, well, this is still looking kind of simple, right? These rules are all one antecedent, and it's maybe we want to do something a little deeper. So one thing we could do is we could enrich this data. I mean, why look at just the cart? There's lots of things, or there's a couple of more things we could try to learn about our customers. And so let's take a slightly different approach.
So instead of just looking at what people bought in their cart, we'll look at what people bought in their cart and when they bought it. So now we have the two features. We have the cart and all the things that were in it, and the date when this purchase was made, which is a date time field. So we can see for this first instance, for example, was on June 3rd of 2015 at 13:06 in the afternoon. And of course, we automatically break this down for you into year, month, day of week, etc. These are all created automatically when we detect a date time field. And so now we can try to find rules that are not only about the items, but might correspond to when the items were purchased as well. We can do a one-click association for this. And so the classic example, which apparently is true, and you can read about this with a little bit of Googling, is a case where Walmart analyzed their data to discover what items people would stock up on before a hurricane, for example. And when they did this, they were expecting to find things like water, batteries, flashlights, etc. When preparing for a major storm. But among the expected items, they found a surprise, which was that demand for strawberry Pop-Tarts increased dramatically, and beer, actually. And now you can try to rationalize this. They're easy to eat, you don't have to cook them, they have long shelf life, lots of calories, etc. But in any event, it was very strongly correlated. If a storm was coming in, then strawberry Pop-Tarts flew off the shelves. And of course, they took action on this. When the next hurricane was coming in, they increased the strawberry Pop-Tarts that were available, and they still sold out.
So we're kind of trying to recreate that a little bit here just by adding the date to our grocery list. And I forgot to mention earlier, but you can actually filter these as well. So I can filter these rules that we've discovered, and I can just put in the keyword date, and now we're only going to see rules that involve the date. Okay, we can look at this first rule that we got, and the day of week is Monday starts at 0. So this is Thursday or Friday. So if the day of week is Thursday or Friday, then the cart includes bottled beer is one of the rules that we've discovered. So as a human rationalizing, perhaps this is people stocking up for the weekend or for watching the game or whatever, but that's a potentially interesting rule. And not only that, but this has a very high coverage as well, right? This is telling you that, it has a high confidence. So this association is actually pretty strong. The leverage and lift are all good too. And there should be at least one rule in here that involves the month. Yes, here it is. So here we have the month between 6 and 9, and that's July, August, or September. Then the cart includes ice cream, and again, we have some pretty reasonable metrics on that as well. So now we can start to see seasonal patterns just by doing the association discovery and having the items that people are buying associated with the date field. All right, so let's do another example. And I want to talk about this idea of medical risk. And so we're going to use this UCI diabetes data set, which is a set of diagnostic measurements for patients. They have things like their blood pressure and stuff, and then they have a field that indicates whether or not that patient had diabetes. And the goal would be to find general rules to indicate diabetes. So why is this? Why would you do this? I mean, this sounds like a problem that would be more of a classification problem. So let's actually start this as a classification problem. So we'll take this data set. All right, and again, you can kind of see the fields we have. We have the number of times this patient was pregnant, what their 4-hour plasma glucose was, their blood pressure, triceps skin thickness, etc. And then we have a Boolean down here that says, yep, that patient had diabetes. Nope, this one did not. All right, and we can create our data set. And now we can just do a one-click model, which will model the diabetes state for us. All right, and now we get a nice tree that has found all of the significant rules that indicate whether or not a patient has diabetes based on these diagnostic measurements, right? So we have a rule here, for example, that, okay, if the plasma glucose is greater than 126 and it's additionally greater than 155 and the BMI is less than this and the age is greater than that, stack all this information on there and we get a prediction of true with a confidence of 70%. And you can kind of browse around this tree and of course this is incredibly useful. I can use this tree to make predictions, right? I can now take a new patient and I can send it into this tree and I can get a prediction out. And you're going to have good, reasonable, accurate answers. The problem with this is it doesn't give you a nice summary view. I mean, what are the risk factors? If I just wanted to talk about plasma glucose, what should I be worried about? What level do I worry about? You don't really get that information here. I mean, you can still drive the information down the tree and get a prediction, but it's not telling you a rule, a simple high-level rule that maybe isn't as accurate, but is easier to understand. All right, so we can actually take this same data set and just run it through an association. And once that's done, we can actually filter this by diabetes equals true, for example. And now we're going to see rules where diabetes is indicated. And so now we get this very nice, easy to understand risk factor, if you will. If your 4-hour plasma glucose is greater than 146, then the consequence is that diabetes is true. And we can understand how likely this rule is, right? So we've got a coverage of 20%. So 20% of our instances in our data set are matching plasma glucose greater than 146. And of those, we have 72% of them also have diabetes true, right? So we can see this is a fairly high quality rule.
That if your 4-hour plasma glucose is greater than 146, then diabetes is true with 72% confident.
I've used confidence twice, but it is worth keeping in mind that they're computed differently, right? The confidence that we use in the tree and the confidence we use in the association discovery are computed differently, and they don't necessarily. You can't read them. This one, 72%, is the same as 72% in the tree. They're computed differently. But we can definitely see from the confidences rule that this is a statistically significant association. All right. So the next feature that I want to introduce as part of our fall release is the partial dependence plots. So these are an extremely useful tool for visualizing the performance of an ensemble over a set of input features. So let's go back to this diabetes data set again, and let's take a little bit closer look at our model. So if we come into the diabetes model, all right, one of the visualizations we have is called the sunburst. And this is a really nice visualization because it gives you a very high-level overview of how this model is performing, right? So I can see this is colored by confidence right now. Where red is low confidence, and I've got this nice arc segment here, which means there's lots of data flowing down there. It's a confident rule, and so I have a very nice visual representation of how the tree is performing. Right, if this whole thing is red, then it's not performing very well. If the whole thing's green, I probably have, well, it's performing well. We'll say that, but maybe you have errors in your data. You never know. And the idea here is that this is really powerful to have these visualizations where you can kind of see the performance over the set of all inputs. And now, if we want to do an ensemble, right, because we know an ensemble is typically going to perform better than a single model. I actually have seen 1 or 2 cases where just doing the one click didn't at least do as well, if not better, than a model. It's just, in general, it reduces the problem of overfitting and you get a better result. But it's hard to visualize now. We've lost this power, right? We can go into each model, but each one of these models is being built with random features and random splits. You can see just looking at them, they're totally different. It's now getting much more difficult to understand what this ensemble is doing over the set of input possibilities. And we can kind of try to play with it a little bit by doing a prediction, right? We can send some data in and see how the trees are voting. But this is still case by case. It's only showing us one example when we do it this way. If I make a prediction and I send data, I can say, oh yeah, for that input data, I get this tree is true, that tree is false. And wouldn't it be nice to extend this idea and say, look, let's just consider 2 variables and ask all the trees to vote over the range of all possible input values and then plot how the ensemble is performing. And that's exactly what this partial dependence plot does. So we can take our ensemble and hit the link for partial dependence plot, and it's going to pick 2 axes to label by using the feature importance. So those are the fields that reduce the error of the tree or the ensemble the most. And in this case, that actually is the 4-hour plasma glucose and the BMI. It's going to choose those as our coordinates. And then for each, over the input range, so we can see here the plasma glucose range is ranging from 0 up to about 200 or so, and the BMI from 0 up to almost 70. And each one of these grids, it's using those 2 as input values, and then asking the ensemble for a prediction, and then counting how many trees vote true or false. And so in this case, looking on the right-hand side there, you can see diabetes vote share is false. So this ensemble is predicting false for a plasma glucose of 24 and a BMI of 8 or so, and all 10 trees agree. So this is giving you a visual representation of the sort of the boundaries in your input data where the tree is having, or the ensemble is having difficulty, or where the ensemble is very confident. And you can see visually where this is happening, right? So here, this little grid up here, you can see there's just 9 out of 10 trees are all agreeing. So there's a little bit of disagreements here. Even if you have low plasma glucose, if you have an extremely high BMI, there's one tree that is decided this is an area where diabetes is more likely true. But still, 9 out of 10 trees say no. Similarly, if we hold BMI low but crank up on the plasma glucose, we can see the trees start to disagree right around a 4-hour plasma glucose of 100. But 1 tree fell out, 2 are falling out. Now we've got 3, and now we're getting to a zone where it's it's turning into a 50-50 almost, but it's still predicting false. But as we start bringing up the BMI, we hit this boundary up here, this black region where it's 50-50, right? So your ensemble really is arguing with itself essentially until you get into this zone up here where diabetes is now true, right? So high 4-hour glucose and high BMI. And of course, we can change these, right? So if we wanted to see this with regards to age, now we can see it doesn't really matter how old you are, okay? If you have a high 4-hour or if you have a low 4-hour plasma glucose, your age is fairly independent, right? This whole zone here, the ensemble's voting false. But as your 4-hour plasma glucose starts to cross into the 110, 120, 130, then the vote is starting to change, right? Now we're false here, 7 out of 10, but all of a sudden now we're true with 6 out of 10. So there's a nice boundary right around here. And again, remember our association discovery rule found, this single rule of plasma glucose greater than 146, which you'll notice is right in this same zone as well. And in fact, if you go through and change pretty much any other variable like diabetes pedigree, which is a measure of how many family history basically, again, you can see this boundary again right around this 140 zone, which is that sort of same rule that association discovery found for us. All right. So the next thing I'm going to talk about is our Flatline Editor. So this is a user interface tool which makes it easy to write, validate, and test flatline expressions. So what is Flatline? Well, Flatline is a domain-specific language for filtering and feature engineering of data sets, which we actually released quite a while ago. It's a great tool for feature engineering, but it was previously really difficult to test these expressions without just trying it. And every time you made a typo or something, that would actually create a failed data set. And so the Flatline Editor is a nice way that documents the format and it kind of guides you into doing it a little bit. And I'm going to do, I see I'm running a little bit behind, so I'm going to speed this up just a touch. So I'm going to show you a very simple example. So if we look at this, this data set is This is a bit of a contrived example, and I'm going to do it really fast, so bear with me. But you can imagine you're building a GPS device, and you just wanted a handy way to predict the dominant direction of a highway based on its highway number. Is that possible even? And so we have these highway numbers like Highway 2 is east-west, or Highway 5 is north-south. And if we just build a tree to do this, which we can do with a one-click model. Whoop, not a one-click, sorry. I was going to do that. I want it to predict the highway direction based on the highway number. Then what's going to happen is we're going to get this what looks like a really complicated tree. And if you look at what some of these rules are, you know, their highway number is greater than 14, less than 96, less than 61, less than 44, less than 43, greater than 26. Then it's north-south. And you can kind of tell by looking at this tree that it's not really learning anything interesting about the highway number other than they have a logical order, right? I mean, 2 comes after 1 and 3 comes after 2. And it's just using these rules to zone in on a specific highway that it knows the answer to and then it tells you. So it hasn't learned anything that really associates highway number to the principal direction. You're just getting what looks like, you know, it's just using these rules to zone in on individual instances. And this is a feature engineering problem. We haven't given the model anything, or the modeling engine anything more than a highway number, and all it knows about numbers is that some are bigger and some are smaller, right? And we actually, what if there was something else about the highway number that we could learn? Well, one of the things is even or odd, which in the U.S. highway system is an indicator. Now, of course, the modeling engine doesn't know that, but we can add that information. If we had the insight, hey, maybe it matters if this is odd or even, we could engineer a new feature that told us whether or not the highway number was odd or even. So we can do that in here by adding a field to this data set. And we would call this is even. And there's lots of things you can do when you're adding a field. So you can do some discretization. If you have a numeric field, you can replace missing values. You can do some normalization. There's lots of mathematic functions. And if one of these built-in functions isn't enough, you can actually do a full Lisp S expression. This allows you now to do basically programmatic feature engineering, right? So I could do something like take the logarithm of one feature and add it to the square of another, or some polynomial expression of all the other features and create a new feature from that. You can even do windows where you can say, look, take this feature at this point and 4 rows later and 6 rows later and combine those, right? We call those time windows or windows. And so this is what I want to do. And if I knew exactly what I wanted to type for my S expression to test for even or oddness, I could just type it into this box. But the Flatline Editor is available by clicking on that little pencil there. And this is going to open the Flatline Editor. And we also have, in addition, a help section down here. And so I have to kind of an idea of what I want to do. So I know I can test even or oddness by computing mod 2, right? That's going to give me 0 or 1, 0 for even, 1 for odd. And so I know I want to take the mod, say, and you notice it turned sort of a purpley color there. That means it actually recognizes that command, right? If I type Mose or something, it stays black. So it's telling me that it knows that's a function. And I can actually look up the function down here in the list of functions and see it as well. If you type part of what you think a function might be and hit Control Space, it'll bring you up a list of all the possible matching functions. And so modulo is definitely one. And now I need a field, so I can just type field, and I see it recognizes that. And now if I type Control Space, it'll actually bring up a list of fields. So oh, okay, I want the highway number. That's perfect. And I want to compute this modulo 2. All right, and that's not quite enough. It'll give me 0 or 1. So additionally, I want to test if it's equal. So I need to add one more expression on here, and I want to say if it's equal 0. And now I can validate this expression, and it gives me an error. I can see, oh wait, there's a end of file while reading invalid expression. So now I can look at my expression. And previously, if I just hit submit, this would create an error. I would have got a black cloud and a failed data set, and I'd have to go back and cut and paste my expression back in and try to get it right. And notice that what I missed was a third parenthesis, right? 1, 2, 3 on the left, 1, 2, 3 on the right. So now I can validate, and it tells me this expression is valid. I can hit preview, and it'll actually take a sample from my data and show me what my new data set is going to look like. So I can see is even is the last feature on there, and I can see when it's 59 is even is false, and when it's 68 is even is true. So that looks correct. So I can accept this expression and create the data set. And now it's actually going to run that flatline rule on my data set, which has created a new feature called is even. And now when I configure my model to predict the direction, I get what I expect here, which is that if is even is false, so it's an odd number, this is a north-south highway, and if is even is not false, so it's true, then this is east-west, which is the dominant feature of the U.S. highway system. North-south highways tend to be are odd-numbered. All right, so just a quick overview of where this fits into our workflow. You can see that the Flatline takes a data set and returns a data set. So it kind of fits in down there. And I need to pick this up a little bit so we have time for questions. So we'll just accelerate a bit, sorry. So the next up, we have a new classification algorithm, which is the machine learning workhorse, logistic regression. So BigML's implementation can transparently handle numeric, categorical, and text features. So it does all that for you. You can just run the logistic regression against your data set and get the results. Even better, the bindings, for example, Python, they support local predictions. So just like our models and ensembles and everything else, you can extract this logistic regression into your local environment and now use it to make predictions without having to pay the latency penalty. And also, BigML supports both of the standard L1 and L2 regularizations. This is currently only available through the API, and the documentation, the API documentation is in that link down at the bottom there. And where this fits in, of course, into our workflow is in the modeling. The only thing to note about logistic regression is that, of course, it's a classification algorithm, right? So the trees are very, very nice about being classification and regression trees, but with the logistic regression, you're, of course, just doing a classification problem there. How do you know which one to use? Single trees, really easy to interpret, robust to missing data. They tend to overfit. Okay, the ensembles, top performers, they're almost always going to do better than everything else. And again, still robust to missing data. A little harder to interpret, although easier now with PDPs. And then for logistic regression, they tend to be a little bit more robust to noise. And another side benefit is that they output what can be interpreted as a probability. So there are some problems where you don't want just a prediction, you actually want a probability. So logistic regression is nice for that. The disadvantages are they don't deal well with missing data, sort of like the clustering algorithm. You need to handle missing data, and of course they're harder to interpret. Right? What does a list of coefficients tell you about your data? Right? It's not giving you any insight into how it's actually making those decisions, unlike the trees, which make it very easy to interpret. All right. So the last thing is the correlations and statistics tests. So this is handy when especially when you're working with a feature-rich data set, which can contain features which are correlated in uninteresting ways. That's one example. So you might have a data set that has your height in feet and meters, right? You don't want to have both of those in there. So you can run a correlation against it. So to create it, you only need to provide a data set and the name of the field to compute the correlations against. And this is going to return you several standard measures such as the Pearson coefficient, the Spearman coefficient. And you can see the list there. There's a detailed description of what all these metrics mean and how to access them. Again, this is currently only available through the API. And then we also have statistical tests. So you can, given only a data set, you can ask it to compute these advanced statistics, which are a little deeper than the summary statistics that we give you in the data set view, including things like Benford's law, which can be useful for fraud detection. This is looking at the distribution of the first digit of numbers, some normalization tests like Anderson-Darling, Jacques-Barra, and Z-score, and of course grubs, which is a very classic way to look for outliers. And again, all you need to do is pass in a data set, ask for the statistical tests, and you get back a nice object that has all these metrics in it. Again, currently only available through the API. And so this is sort of an overview of our workflow and all of the areas where we've added new stuff, right? So we've got logistic regression in our classifiers. We have a completely new algorithm in the association discovery. We have a completely new set of things you can do with the data set and the statistical tests and correlations. And of course, we've made Flatline and therefore feature engineering, which is extremely important. We've made that even easier. And as you can tell, there's a lot of green in this slide. So we've brought a lot of features in this release. Of course, there's lots of smaller things that we're constantly improving, but the introduction of association discovery is a significant step forward in BigML's vision to build the world's premier cloud-based machine learning platform. And you can expect to see more algorithms as we continue to build out carefully curated, effective algorithms and data mining techniques that have proven their mettle on real-world problems. So stay tuned. We are not done revolutionizing the world of machine learning.